The morning of June 4th, 1942, 15,000 feet above the Pacific Ocean, Lieutenant Richard Best rolled his Douglas SBD Dauntless into a 70-degree dive. Below him, the Japanese carrier Akagi zigzagged through the cobalt water, her flight deck crowded with aircraft being armed and fueled. Best reached for the dive brake handle mounted to the right of his seat and pulled. The response was immediate and violent. Massive perforated flaps, each one the size of a basketball court section, thrust outward from the trailing edges of his wings, both above and below. The hydraulic actuators held them against an impossible force, air screaming past at over 400 miles per hour, generating thousands of pounds of pressure trying to rip those flaps back into the wings. But they held. The Dauntless shuddered, then steadied into a rock-solid platform. Best's dive speed, which moments before had been accelerating toward a lethal velocity, locked at 250 knots. He had time now. Time to adjust. Time to aim. Time to change the course of the war. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. That those dive brakes held, that they didn't collapse under the aerodynamic forces, that the hydraulic system didn't fail, that Best could make minute corrections all the way down to bomb release, was the culmination of an engineering problem that had nearly killed the SBD program 3 years earlier, and the solution had required someone at Douglas Aircraft in El Segundo, California, to do something that seemed, to conventional engineering wisdom, utterly insane. To understand what made this so remarkable, you have to understand what those dive brakes were actually fighting against. When an SBD entered a steep dive, it wasn't simply falling. The Wright R1820 Cyclone engine was still producing 1,200 horsepower, gravity was accelerating the 10,000-pound aircraft downward, and the Pacific air was flowing over those wings at velocities that could tear fabric, buckle aluminum, and turn control surfaces into crumpled metal. Without dive brakes, an SBD in a 70-degree dive would accelerate past 350 miles per hour, then 400, then beyond the aircraft's structural limits. The wings would fold. The pilot would black out from the G-forces required to pull out. The entire concept of precision dive bombing would become impossible. The dive brake's job was to create drag, enormous, sustained drag without destabilizing the aircraft. Solid flaps would work, but they'd cause turbulent buffeting that would shake the tail assembly apart and make accurate aiming impossible. So Ed Heinemann's design team at Northrop, and later at Douglas after the corporate takeover in 1937, had developed perforated split flaps. Hundreds of 3-inch holes drilled through, the metal allowed air to flow through in a controlled pattern, maintaining stability while still generating massive drag. But here was the problem that emerged during testing of the early models. Those flaps had to deploy outward into the airstream, and once deployed, they had to stay deployed against aerodynamic forces that increased exponentially with speed. At 200 miles per hour, the pressure trying to force those flaps back into the wings was manageable. At 250 miles per hour, it was severe. At 300 miles per hour speeds that dive bomber pilots were routinely reaching, as engines grew more powerful and dive angles grew steeper, the forces became monstrous. The BT-1, the Northrop dive bomber that preceded the SBD, had hand-cranked dive brakes. Pilots would manually extend them using a mechanical crank before entering the dive. It was slow, it was exhausting, and at high speeds, it was often impossible. The flaps simply wouldn't extend against the airstream pressure, or worse, they'd partially extend and then jam, leaving the pilot with asymmetric drag and an uncontrollable aircraft spiraling toward the ocean. Heinemann knew that the future belonged to hydraulic systems. Use pressurized fluid to extend the flaps quickly and hold them rigidly in position. The US Navy agreed. When Douglas took over the program and began developing what would become the SBD Dauntless, hydraulic dive brakes were a non-negotiable requirement. The question was, how much pressure would the system need? standard hydraulic systems in aircraft of the late 1930s operated at around 500 to 800 pounds per square inch. That was sufficient for retracting landing gear, which faced minimal aerodynamic resistance. It was adequate for moving control surfaces like ailerons and rudders, which were designed to work with the airflow, not against it. But dive brakes were different. They were fighting the full force of the slipstream. And, as testing began on the XBT-2 prototype in 1938, it became clear that 800 psi wasn't going to cut it. During test dives, pilots reported that the dive brakes would extend initially, but as speed increased, they could feel them giving way. The hydraulic actuators couldn't maintain pressure against the aerodynamic forces. The flaps would start to retract partially, creating asymmetric buffeting. In one terrifying test flight, the dive brakes collapsed entirely at high speed, and the test pilot barely pulled out of the dive before exceeding the aircraft's structural limits. The Navy's feedback was blunt: fix this, or the entire program is in jeopardy. Back at the Douglas facility in El Segundo, Heinemann's engineering team confronted a problem that conventional wisdom said couldn't be solved within the constraints of a carrier-based aircraft. Increasing hydraulic pressure meant heavier pumps, heavier reservoirs, heavier actuators weight that a Navy dive bomber, which had to take off from a short carrier deck with a full bomb load, simply couldn't afford. There were fundamental trade-offs between system pressure, system weight, and structural integrity. But there was another engineer on the team working in the hydraulics section, studying the problem from a different angle. His analysis showed something that the broader aviation industry hadn't fully appreciated. The relationship between pressure and actuator holding force wasn't linear at these extremes. If you could boost the system pressure high enough, you could actually use smaller, lighter actuators, because the pressure would be so intense that the hydraulic fluid itself would act almost like a solid mechanical lock. The flaps wouldn't be held in place by the mechanical strength of the actuator arms, they'd be held by what was essentially a column of incompressible fluid under such extreme pressure that it couldn't budge. The proposal was to more than double the hydraulic pressure, push it well beyond 1,000 pounds per square inch, potentially as high as 1,200 or even 1,500 psi. At those pressures, the entire system would need to be redesigned. Every seal, every line, every fitting would have to withstand forces that were, in the context of 1939 aircraft design, genuinely extreme. There was real concern about catastrophic failures. A hydraulic line rupturing at 1,500 psi could spray fluid with enough force to penetrate aluminum sheet metal. A seal failure could cause explosive decompression, and if the system failed during a combat dive, the pilot would lose his dive brakes entirely, potentially fatal. The conservative engineering choice would have been to incrementally increase pressure, add mechanical locks, or redesign the dive brakes to be smaller and less effective, but easier to hold in position. But Heinemann understood what was actually at stake. This wasn't just about one aircraft feature. This was about whether the US Navy would have a dive bomber capable of precision strikes against capital ships, the aircraft carriers and battleships that would determine the outcome of any Pacific War. The Navy needed an aircraft that could dive steeper, faster, and more accurately than anything Japan or Germany possessed. Half measures wouldn't accomplish that. The decision was made: push the hydraulic pressure to the limit. Douglas engineers began a complete redesign of the SBD's hydraulic system for what would become the SBD-3 variant. Every component was upgraded. Pumps were reinforced. Lines were replaced with heavy-duty specifications. Seals were redesigned using new high-pressure gasket materials. The actuators themselves were re-engineered to handle the increased forces, and critically, relief valves and pressure regulators were installed to prevent catastrophic overpressurization if something went wrong. The testing phase was nerve-wracking. Early tests in 1940 revealed minor leaks and fitting failures that had to be corrected. But as the system was refined, something remarkable became apparent. It worked. The dive brakes deployed rapidly and held solid, even at speeds approaching 300 miles per hour. Pilots reported that once the brakes were extended, they felt locked in position. There was no give, no gradual collapse, no buffeting from asymmetric deployment. The SBD's dive became what Heinemann had envisioned, a stable, controlled descent that gave the pilot time to track a moving target and release his bomb with precision. By early 1941, the SBD-3 entered production with its improved hydraulic system. The technical specifications were impressive. The dive brakes, when fully deployed, created enough drag to limit terminal velocity to approximately 250 knots, 288 miles per hour in a 70 to 80 degree dive. That was slow enough to keep the aircraft well within its structural limits and give the pilot plenty of time to aim. Yet the SBD could still accelerate rapidly once the brakes were retracted and the pilot began his pullout, using that massive right cyclone engine to claw back to altitude or evade enemy fighters. The perforations in the flaps were equally critical. Those hundreds of 3-inch holes weren't just for show. They allowed air to flow through in a controlled pattern that eliminated the turbulent vortices that would otherwise form behind solid flaps. This meant the tail assembly remained stable even with the brakes deployed. Pilots could make fine control inputs throughout the dive, adjusting their aim right up to the moment of bomb release. It was this combination hydraulic power to hold the brakes against extreme forces and aerodynamic design to maintain stability that gave the SBD its legendary accuracy. There was one more element that made the system work: the bomb displacement gear, or trapeze, as pilots called it. When a pilot released his bomb during a near-vertical dive, the bomb would initially be traveling downward at the same speed as the aircraft over 250 miles per hour. Without the trapeze, that bomb would simply slam into the propeller. The solution was a hydraulically actuated swing arm that would grab the bomb as it released from the fuselage rack and physically swing it forward and downward, ensuring it cleared the propeller arc before falling free. This too required the high-pressure hydraulic system because the forces involved in rapidly swinging a 1,000-pound bomb clear of the aircraft during a high-speed dive were substantial. By the time the SBD-3 reached frontline squadrons in the spring of 1941, American naval aviators had a weapon unlike anything else in the world. The German Junkers Ju-87 Stuka could dive steeply, but its dive brakes were less sophisticated, and its overall performance was inferior. The Japanese Aichi D-3A Val dive bomber was an excellent aircraft, but it lacked the SBD's structural strength, and its dive brakes were less effective at maintaining controlled speeds. Neither would prove as accurate or as survivable in combat as the Dauntless. But no one fully appreciated just how crucial those improvements would be until June 4, 1942, when 54 SBD Dauntless dive bombers from the carriers Enterprise and Yorktown arrived over the Japanese carrier fleet near Midway Island. The Japanese carriers had been caught in the worst possible position. Their flight decks were crowded with aircraft being rearmed and refueled after striking Midway Island. Bombs, torpedoes, and aviation fuel covered the decks. The combat air patrol of Zero fighters that should have been protecting the fleet was down at sea level, having just finished massacring the American torpedo bomber squadrons. And now, from 15,000 feet, came the SBDs. Lieutenant Commander Wade McCluskey led the first wave from Enterprise 33 aircraft from Bombing Squadron 6 and Scouting Squadron 6. They arrived over the Japanese fleet at precisely 10:22 in the morning. McCluskey's voice crackled over the radio. Attack! The Dauntlesses rolled into their dives almost simultaneously, a cascading sequence of aircraft tipping over and plunging downward. What happened next demonstrated exactly why those hydraulic improvements had been so crucial. Each pilot reached for his dive brake handle and pulled. Across the formation, perforated flaps thrust into the slipstream. The hydraulic systems, pressurized to their extreme limits, holding against forces that would have torn lesser mechanisms apart, locked those flaps in position. 54 aircraft stabilized into controlled near-vertical descents. Inside the cockpit, the pilots experienced what their training had prepared them for, but combat made visceral. The dive was loud, the wind roaring past the perforations in the purser. Flaps created a distinctive screaming sound that Japanese sailors would later describe as terrifying. The aircraft shook from the massive drag forces, but remained stable. The telescopic bomb sight mounted above the instrument panel gave each pilot a magnified view of his target. And most importantly, they had time. The dive brakes were holding. The aircraft weren't accelerating into an uncontrollable plunge. They could aim. Lieutenant Dick Best, leading 5 aircraft from Bombing 6, selected the carrier Akagi, the flagship of the Kido Butai, Admiral Nagumo's elite carrier strike force. Best's section dove through moderate anti-aircraft fire. Black puffs of flak burst around them, and tracers arced upward, but the speed and angle of their descent made them difficult targets. Best held his dive steady, making minute adjustments with his stick and rudder pedals. The dive brakes gave him a stable platform. His bomb sight crosshairs tracked across Akagi's flight deck, compensating for the carrier's turns. At 2,500 feet, Best released. The 1,000-pound bomb fell away. The trapeze swung it clear of the propeller arc. Best immediately reached for the dive brake handle and retracted the flaps, then hauled back on the stick, pulling out of the dive. The G-forces pressed him into his seat. The SBD was stressed to withstand 9 Gs, and Best was using most of that margin. Behind him, his rear gunner, aviation radioman James Murray, watched their bomb track downward. It struck Akagi's flight deck just aft of her midship elevator. The explosion detonated armed bombs and torpedoes on the hangar deck below. Within seconds, Akagi was engulfed in flames. A second bomb from Best's section struck moments later near the stern. The flagship of the Japanese carrier force was mortally wounded. She would burn for hours before being scuttled that evening. Simultaneously, Lieutenant Commander Maxwell Leslie's squadron from Yorktown attacked the carrier Soryu, 17. Dauntlesses dove through increasingly heavy anti-aircraft fire. Leslie himself had lost his bomb to an electrical malfunction before the dive, a bitter irony, but his squadron pressed the attack. 3 bombs struck Soryu in rapid succession. 1 penetrated to the hangar deck and detonated among fully fueled aircraft. The resulting explosions blew out the carrier's sides. Soryu would sink that afternoon. The third carrier, Kaga, came under attack from the remaining aircraft of McCluskey's force. At least 4 bombs struck her flight deck. 1 penetrated near the island structure and detonated in the upper hangar, triggering catastrophic secondary explosions. Another hit near the forward elevator, blowing burning aviation fuel across the forward flight deck. Kaga's damage control parties fought the fires for hours, but she was doomed. She would sink that evening. In less than 6 minutes, 3 of the 4 Japanese carriers at Midway had been fatally damaged. The 4th carrier, Hiryu, would be found and destroyed by SBDs from Enterprise later that afternoon. The decisive battle of the Pacific War had been won by dive bombers whose hydraulic systems held under combat conditions that would have been impossible 3 years earlier. The pilots who flew those missions would later describe the experience of the dive itself in terms that revealed just how critical the technical improvements had been. They spoke of the confidence that came from knowing the aircraft would respond. The dive brakes would deploy when needed. They would hold against the massive aerodynamic forces. The aircraft would remain stable and controllable all the way down to bomb release. That confidence translated directly into accuracy. When a pilot knew his aircraft would perform, he could focus entirely on the target, on the wind, on the timing of his release. Compare this to the experience of other nations' dive bombers. German Stuka pilots flew an aircraft with automatic dive brakes that would deploy and even pull the aircraft out of the dive if the pilot blacked out an impressive safety feature. But the Stuka's overall performance was limited. It was slow, vulnerable to fighters, and its dive brakes were less effective at maintaining a consistent terminal velocity. Japanese VAL pilots flew a maneuverable aircraft, but its dive brakes were inferior to the SBD's, and it lacked the structural strength to consistently survive the stresses of combat operations. The SBD's combination of high-pressure hydraulics, perforated flaps, and robust construction created something unique, a dive bomber that was both highly accurate and operationally reliable. This wasn't just a matter of pilot skill, though American naval aviators were superbly trained. It was a matter of engineering. The hydraulic system worked, the dive brakes held. The aircraft did what it was designed to do, consistently, even under the extreme conditions of combat. After Midway, the SBD Dauntless continued to prove its worth throughout the Pacific Campaign. During the Guadalcanal Campaign from August 1942 through February 1943, SBDs operating from both carriers and the Henderson Field airstrip on Guadalcanal itself flew thousands of sorties. They attacked Japanese warships during the numerous naval battles around the Solomon Islands, the Eastern Solomons, Santa Cruz, and the naval battle of Guadalcanal. They provided close air support to Marines fighting in the jungle. They conducted anti-submarine patrols, and in every role, the reliability of those hydraulic systems and dive brakes was essential. Maintenance crews on carriers and at forward bases developed deep expertise in servicing the hydraulic systems. They learned to detect leaks before they became critical. They became expert at bleeding air from the lines and replacing seals. They understood that the high-pressure system required meticulous attention. A small leak at 1500 psi could drain the reservoir rapidly, but they also understood that when properly maintained, the system was remarkably reliable. Unlike the complex mechanical systems of some aircraft, the SBD's hydraulics were relatively straightforward. A pump, a reservoir, lines, actuators, and control valves. There were no exotic materials, no proprietary components that couldn't be fabricated in a field workshop if necessary. This maintainability was crucial to the SBD's success in the harsh conditions of the Pacific. Carriers were essentially mobile repair shops, but they had limited space and limited spare parts. Aircraft that required exotic maintenance or frequent repairs couldn't sustain high operational tempos. The SBD could. Its hydraulic system, despite operating at what were considered extreme pressures, proved to be both durable and maintainable. Mechanics could service it with standard tools. Replacement parts, when needed, could be fabricated from standard stock. And the system rarely failed. Catastrophically, leaks were usually slow enough to be detected during pre-flight checks, and partial failures typically left the pilot with some hydraulic function rather than none. There's a broader lesson here about the relationship between engineering boldness and operational success. The decision to push hydraulic pressure beyond conventional limits in the late 1930s was a calculated risk. It required redesigning the entire system. It added complexity and potential failure modes. Conservative engineers argued for safer, more incremental approaches. But Heinemann and his team understood that incremental improvements wouldn't deliver the performance the Navy needed. They needed a dive bomber that could operate in conditions that would destroy lesser aircraft, and sometimes achieving that requires pushing past conventional engineering wisdom. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The hydraulic breakthrough in the SBD also influenced subsequent American aircraft design. The lessons learned about high-pressure hydraulic systems, about the relationship between pressure and actuator efficiency, about the importance of maintainability, even in extreme performance systems, these lessons were applied to later designs. The Curtiss SB-2C Helldiver, which was intended to replace the SBD, used an even more advanced hydraulic system. The Grumman TBF Avenger torpedo bomber benefited from similar design principles. By the end of World War II, high-pressure hydraulics were standard in American military aircraft, but the SBD had been one of the pioneers in proving the concept under combat conditions. The specific engineer, or engineers who championed the high-pressure hydraulic solution for the SBD, remain somewhat obscure to history. Ed Heinemann gets deserved credit as the overall design lead, but engineering teams are collaborative efforts. Someone in Douglas Aircraft's hydraulics section in El Segundo did the calculations, ran the tests, argued for the solution, and made it work. That person's name may not appear prominently in the history books, but their contribution was fundamental to the aircraft that changed the course of the Pacific War. Consider the alternative timeline. What if the hydraulic system hadn't been improved? What if the SBD-3 had entered service with the same 800 psi system as earlier models? Combat operations would have revealed the limitations quickly. Dive brakes failing at high speeds, pilots forced to shallow their dives, reducing accuracy. Increased losses to anti-aircraft fire because aircraft would need to dive from lower altitudes to hit targets. The precision that allowed SBDs to destroy 4 carriers at Midway might never have been achieved. The battle's outcome could have been different. The entire Pacific campaign might have taken a different course. This is the hidden influence of engineering decisions. Most people who know about the Battle of Midway can tell you about the brave pilots, the intelligence breakthrough that located the Japanese fleet, the courage of the torpedo bomber crews who died drawing Japanese fighters down to sea level. Far fewer know about the hydraulic system that allowed the dive brakes to work. Yet without that system functioning exactly as designed, none of the rest matters. By 1943, as the SBD began to be replaced by the Helldiver in carrier squadrons, Marine Corps squadrons resisted giving up their Dauntlesses. Marine pilots loved the SBD. They found it more reliable than the Helldiver, easier to land, and more forgiving of pilot error. Part of this preference was the hydraulic system. It just worked. The dive brakes deployed when needed, held when needed, and retracted when needed. Pilots trusted the aircraft because the aircraft consistently performed. The last combat sorties flown by SBD Dauntlesses occurred in August 1945, as Marine squadrons supported the final operations of the Pacific War. By then, the aircraft was thoroughly obsolete by the standards of late-war aviation. Newer aircraft were faster, could carry heavier loads, and had more advanced systems. But the SBD had done its job. From December 1941 through August 1945, Dauntlesses had sunk 6 Japanese aircraft carriers, 14 cruisers, 6 destroyers, and 15 transport or cargo ships, plus numerous smaller vessels and shore installations. No other Allied bomber in the Pacific came close to that record. That combat record rested on many factors: pilot training, tactical doctrine, intelligence support, carrier operations, maintenance, logistics. But at the foundation was an aircraft that worked, an aircraft whose dive brakes deployed and held, even when hydraulic actuators were fighting thousands of pounds of aerodynamic pressure, an aircraft whose engineers had made a bold decision in the late 1930s to push hydraulic pressure beyond conventional limits, and whose decision had been vindicated in the most demanding test environment imaginable: combat. The engineering insight that made the SBD's dive brakes reliable didn't end with the Dauntless. It rippled forward through decades of aviation development, influencing how engineers thought about the relationship between hydraulic pressure, component weight, and system reliability. But perhaps more importantly, it demonstrated a fundamental principle that applies far beyond hydraulics. Sometimes, the path to reliability runs through what appears to be extreme complexity. After the war, Ed Heinemann continued his remarkable career at Douglas Aircraft. He led the design of the AD Skyraider, a single-seat attack aircraft that became legendary in Korea and Vietnam for its ability to carry enormous bomb loads and absorb battle damage. The Skyraider's hydraulic systems incorporated lessons learned from the SBD, using high-pressure systems to operate massive dive brakes and control surfaces. Heinemann later designed the A3D Sky Warrior, the heaviest aircraft ever regularly operated from aircraft carriers, and the A4 Skyhawk, an exceptionally lightweight jet attack aircraft. Each of these designs reflected principles first proven in the SBD, that bold engineering choices, properly executed, deliver operational advantages that incremental improvements cannot match. The specific hydraulic pressures used in the SBD-3's dive brake system became something of an industry reference point. When other manufacturers designed dive brakes or air brakes for high-performance aircraft, they studied the Dauntless. They examined how Douglas had managed the engineering trade-offs between pressure, weight, and reliability. They learned from the SBD's maintenance record in combat conditions. The aircraft had essentially served as a 4-year operational test program under the most demanding conditions imaginable. But there's another dimension to this story that reveals itself when you talk to the men who flew the SBD in combat. Their accounts focus on trust. They trusted the aircraft. They trusted that when they pulled the dive brake handle, the flaps would deploy. They trusted that the hydraulic system wouldn't fail at the worst possible moment. And this trust translated into effectiveness. A pilot who trusts his aircraft is a pilot who can focus entirely on the mission, on finding the target, calculating the wind, timing the release, evading the defenses. A pilot who doubts his equipment is constantly monitoring for failures, second-guessing, holding back. This psychological dimension of engineering reliability is rarely discussed in technical histories, but it's fundamental to understanding why some weapons succeed and others fail. The German Stuka had automatic systems that could save a pilot who blacked out during pull-out, an impressive technical feature. But those same automatic systems sometimes malfunctioned, and pilots learned to distrust them. The Curtiss Helldiver, which replaced the SBD in carrier squadrons, had better performance on paper, but suffered from numerous mechanical problems early in its service life. Pilots who had flown the Dauntless resented being forced to transition to an aircraft they considered less reliable. The SBD's reputation for reliability stemmed directly from engineering decisions like the hydraulic system upgrade. The engineers at Douglas understood that adding pressure wasn't just about making the dive brakes hold, it was about making them hold consistently, predictably, every time. This required not just designing the system to handle the pressure, but designing it to fail safely if something went wrong. Relief valves prevented overpressurization. Redundant seals prevented catastrophic fluid loss. The control valve allowed pilots to partially deploy the brakes if needed. Every element was engineered for operational reliability, not just peak performance. Consider the alternative approaches that could have been taken. Mechanical locks that would engage once the dive brakes reached full deployment. Smaller dive brakes that would be easier to hold in position. Different perforation patterns that would reduce aerodynamic pressure on the flaps. Each of these approaches had advocates during the design process. Each would have been easier to implement than redesigning the entire hydraulic system for high pressure. But each would have compromised performance in ways that mattered in combat. Mechanical locks add weight, complexity, and failure modes. What happens if the lock engages partially or fails to release when the pilot needs to retract the brakes? Smaller dive brakes mean less drag, which means higher dive speeds, which means less time to aim, and higher structural stress during pullout. Different perforation patterns might reduce the pressure on the flaps, but they also affect the turbulence characteristics and could make the dive less stable. The high-pressure hydraulic solution was difficult, but it was the only approach that delivered the full combination of performance characteristics the Navy needed. This pattern, choosing difficult solutions that deliver complete capability over easier solutions that deliver partial capability, appears throughout the history of successful weapons development. The Manhattan Project didn't pursue the easiest path to an atomic bomb. It pursued multiple difficult paths simultaneously to ensure success. The Apollo program didn't use simple, proven technologies. It developed new technologies because getting to the moon required capabilities that didn't exist. The SBD's hydraulic system operated on the same principle. If you need performance that exceeds existing capabilities, you must be willing to push past existing engineering limits. The maintainers who kept SBDs operational in combat zones understood this, implicitly. They knew they were working on a system that operated at extreme pressures. They knew that every fitting, every seal, every line had to be perfect, and they took pride in that. Aircraft that returned from combat missions with hydraulic fluid leaking from battle damage would be swarmed by mechanics who would trace every line, replace every damaged component, bleed the system, and test it until it was perfect. They understood that pilots' lives depended on that hydraulic system functioning exactly as designed. There's a story, possibly apocryphal, but widely told among SBD veterans about a mechanic at Henderson Field on Guadalcanal who noticed a slow hydraulic leak during a pre-flight inspection. The pilot was already in the cockpit, ready for a critical mission. The mechanic grounded the aircraft, insisted on replacing a suspect fitting, and held the mission until the repair was complete. The pilot was furious at the delay, but when that pilot returned from the mission, he sought out the mechanic and thanked him. During the dive, under maximum stress, that fitting had held. A weaker fitting might have failed catastrophically. The mechanic's insistence on perfection had potentially saved the pilot's life. Whether that specific story is true or not, it illustrates a broader truth about the relationship between engineering and operations. The engineers who designed the high-pressure hydraulic system created the capability. The mechanics who maintained it preserved the capability, and the pilots who trusted it employed the capability. All three elements were necessary for success. By the time production of the SBD ended in July 1944, Douglas Aircraft had built 5,936 Dauntlesses. They had served on every American aircraft carrier in the Pacific. They had operated from island airstrips, often under primitive conditions. They had flown in tropical heat, in freezing high-altitude cold, in torrential rain, and through salt spray. And throughout this service, the hydraulic systems that powered their dive brakes maintained a remarkable reliability record. This wasn't luck, it was engineering. The Japanese military never developed a direct equivalent to the SBD. Their Val dive bomber was effective early in the war, but it lacked the Dauntless's structural strength and sophisticated dive brake system. As the war progressed and Japanese carrier aviation was decimated by losses at Midway, the Coral Sea, and subsequent battles, they never rebuilt the capability that the SBD represented. Part of this was industrial. Japan lacked America's manufacturing capacity, but part of it was technical. The engineering insights that made the SBD work weren't obvious or easy to replicate. The Germans, despite having pioneered dive bombing with the Stuka, also never developed an aircraft with the SBD's combination of accuracy, survivability, and operational reliability. The Stuka was devastatingly effective in the early years of the war against limited opposition, but it proved vulnerable to modern fighters, and its performance characteristics were inferior to the Dauntless. By the time Germany might have developed a successor, the Luftwaffe's focus had shifted to other priorities, and the opportunity was lost. This left the SBD in a unique position. It was the only truly effective carrier-based dive bomber operated by any nation during the critical middle years of World War II. And that effectiveness stemmed from 100 engineering decisions, large and small, that went into its design. The hydraulic system was just one element, but it was a critical one. Without those dive brakes functioning reliably, all the other advantages of the SBD, its rugged construction, its stable dive characteristics, its excellent visibility would have been compromised. Looking back from the vantage point of 8 decades, it's tempting to see the SBD's success as inevitable. The United States had superior industrial capacity, better trained pilots, and eventually overwhelming numerical superiority. But in June 1942 at Midway, none of those advantages were yet decisive. The battle was won by a relatively small number of aircraft, 54 SBDs, flown by pilots who had exactly one chance to get it right. And they got it right because their aircraft worked. That morning of June 4th, when Lieutenant Richard Best rolled into his dive above the Akagi, he wasn't thinking about hydraulic pressure specifications or engineering trade-offs. He was thinking about his target, his altitude, his airspeed, the movements of the carrier below him. But the reason he could focus entirely on those tactical considerations was because the technical considerations had been solved. Someone at Douglas Aircraft, years earlier, had done the engineering work that made that moment possible. The bomb that destroyed Akagi fell for approximately 10 seconds after release. During those 10 seconds, the outcome of the Pacific War hung in the balance. The bomb was guided only by gravity and its initial trajectory. There were no sophisticated guidance systems, no corrections, just ballistics and the skill of the pilot who had released it. But that pilot had been able to aim precisely because his aircraft had remained stable and controllable throughout the dive. And his aircraft had remained stable and controllable because perforated dive brakes, held in position by hydraulic actuators pressurized to over 1,000 pounds per square inch, had regulated his descent. 10 seconds, one bomb, one carrier destroyed, and behind that moment, invisible to everyone except the engineers who had designed it, was a hydraulic system operating exactly as intended under combat conditions that would have seemed impossible to predict years earlier. This is the hidden structure beneath historical events. We remember the battles, the commanders, the strategic decisions. We remember that Midway was a turning point, that American naval aviation proved decisive, that brave pilots changed the course of the war. All of this is true. But beneath this visible history is another layer. The engineering decisions, the technical innovations, the seemingly minor improvements that made the visible history possible. The engineer who pushed for higher hydraulic pressure in the SBD's dive brake system probably never flew in combat. Their name appears on technical documents and patent filings, not in history books or war memorials. They solved a problem that most people never knew existed, and in solving that problem, they contributed to victory in ways that are difficult to quantify but impossible to dismiss. Every time an SBD pilot pulled the dive brake handle and felt those massive flaps lock into position against the screaming slipstream, he was benefiting from that engineer's work. Every time a pilot tracked his target through the telescopic sight, making minute corrections all the way down to bomb release, he was employing a capability that bold engineering had created. Every time a bomb struck exactly where the pilot had aimed it, destroying a carrier or a cruiser or a supply ship, the success could be traced back to technical decisions made years earlier. We celebrate the pilots, as we should. They were brave, skilled, and they risked everything. But we should also remember the engineers. They created the tools that brave men use to win battles. They made the difficult technical choices that translated into operational advantages. They pushed past conventional engineering wisdom when necessary, and they built systems that worked when everything depended on them working. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.